All right, so we were just talking about pitch and frequency, how the pitch of a sound is based on its frequency. Remember we had this relationship between the speed of a wave, the frequency of a wave, and the wavelength of a wave. The speed of a wave is dependent only upon the medium, and then the frequency gives us the pitch of the wave, if it's a sound wave that is, and then the wavelength too is related to the frequency. Now that is that if I have a small frequency, I have a big wavelength, and vice versa. They're inversely related. We'll see that when it comes to closed and open pipes. Let's see. We're going to look at the Doppler effect. You're probably aware of the Doppler effect, or you've at least witnessed it before, right? The Doppler effect is that, say for example, you have a police car coming towards you at a certain speed, and he has a siren on, and it's like, that sound that it makes. As he approaches you, the frequency of the sound goes what? Does it go up or go down? It goes up, right. And then as it goes away from you, it goes down. I know, I'll just see what everybody else said. So the Doppler effect, which we also see in light, is that as the source moves towards you, the frequency increases, the frequency of your sound, and then as it moves away from you, the frequency decreases. They give an equation in your book for this perceived frequency of the sound. It looks like this. The frequency, this is the frequency that you perceive, is equal to the actual frequency times the speed of the wave plus or minus the speed of the what bit did he stand for? I forget. Yeah, the detector. So this is the detector divided by the speed of the wave minus or plus the speed of the source. So for example, this would be like, you know, the police car, and this would be your speed. And then this speed is the speed of the wave, and then this is your frequency. They give this sort of mnemonic where the top sign is for towards, top is towards, and bottom is away, or excuse me, bottom sign is for away. So for example, if you have, you know, here's your police car. If it's traveling in this direction and you're standing over here, that's going to be towards you, and so you would take the top side. You would have plus here, and then you would also have minus here. Okay? However, that's a little bit confusing. I find there's an alternate expression for this, where usually your detector is not moving at all. So you could just say, well, I'm just going to leave this off, because usually our detector, we're staying, you know, we're staying stationary. And so you can just rewrite this as the frequency equals your frequency times the velocity of the wave divided by the velocity of the wave plus or minus the velocity of the source of the wave. And then don't worry about the plus or minus. Just, you know, if the frequency is going to increase or decrease based on, you know, is it moving towards you or away from you? And then you just pick the appropriate sign to make that happen. Y'all follow what I'm saying? That if the frequency is going to decrease, then you know that this has to be plus or minus here. If your frequency is decreasing, now be careful, if our frequency is decreasing, that means I need a big number here. All right? If my frequency is increasing, I need a small number here. All right, so sort of deal with that as you come into it with problems. Yeah.
Frequency is decreasing. Does that mean that car is coming towards you?
If it's decreasing, that means it's moving away from you. Okay. There's further even a simpler version of this. You know, usually on the MCAT, they give you the equations or the various relationships. So It's really a matter of just sort of knowing how this works and being able to deal with it. But there is an approximation which says that V over the this is the velocity of the source divided by the velocity of the wave is equal to my change in frequency over the frequency of the source. I don't know if you'll use that, but it is a little bit easier to deal with. All right, but for now, we'll just sort of stick with this, where our frequency, our new frequency, is equal to the frequency of the source, the actual frequency of the object, times the velocity of the wave divided by the velocity plus or minus the velocity of the source. Let's just try this in some problems. Yeah, that's what.
If my frequency is increasing, that means that I'll have a lower value for the part.
I'm sorry, what?
If my frequency is increasing, that means I'll have a lower value of this subtraction.
Right. So if your frequency is going to increase, you want this to be a small number. So this would be V minus Vs. And then that would make this a big number over a small number, which would cause your perceived frequency to increase. Let's try a couple problems. So on your sheet, let's try 746. This is on your second page. This one right up here. Go ahead and do that 746. It's on the second page. I'll pull up the clicker base. Go ahead and do 747 if you finish 746. But guys, do y'all have your page from last week? Megan, Malcolm? You have the paper from last week? Good. Huh? Okay, doing 746. If the source moves in the direction of the stationary observer hears the waves at a greater what? All right, so a few more seconds. I'll stop at 18. We have 7 people here. Somebody not clicking? Okay, all right. Okay, awesome. Low ball one. So let's try 747. The speed of sound in air is 340 meters per second. The sound from a jet moving through the air at 100 meters per second. So the jet is at 100 meters per second. What now is the speed of the wave? All right, I'll stop at, say, 50. Okay, y'all did a little better than I thought you would. The right answer is B there. It's kind of tricky because you think, well, gosh, this thing is moving, and so I'm going to perceive the frequency to be what, higher or lower from this jet? Let's say it's moving towards me. Actually, it doesn't matter. If it's moving towards you, you're going to perceive it higher. If it's moving away from you, you're going to perceive it lower. And so you think, gosh, if the frequency changes, since I know that V is equal to F times lambda, if the frequency changes, then the speed must change as well, right? But that's not the case. The speed only changes if you change the medium. Actually, what happens is, if our frequency, say, decreases, then our wavelength will increase. So what happens physically in these waves is that the frequency changes, but then the wavelength also changes. But the speed of the wave remains constant. That's not really intuitive, but it's true nonetheless that our speed, unless our medium changes, will always be the same. Let's try number 756. try doing this one. If you finish this one, go on and do 759. I think I'll look at 759. And we'll stop this at about, say, 120, 120. All right, awesome. Okay. All right. A is the right answer. Very good. So here we're going to say that our observed frequency is equal to our actual frequency times the speed of the wave divided by v, what was it, minus plus, I'm just going to write it as plus or minus, times the speed of the source. Here we're looking for what in this equation? Vs, right. So we're looking for this value. I know everything else. I know that f prime is 1100 equals to 1000 times the speed of the wave, which is 340, divided by 340 plus or minus Vs. Which is it going to be? Is the car moving towards or away from us? Okay, it is moving towards us. So I want, if this is going to cause this value to get bigger, what is this going to be? Plus or minus? It's going to be a minus here, right? So you can try to remember that mnemonic, and that's okay, the whole top-bottom bit, but I find it easier just to do that. Just think about the context of the situation. All right, so we have 1100 over 1000 equals 340 over 340 minus Vs. 1100 over 1000, that's 1.1, and 40 over 340 minus Vs. We could probably just step away here and look at our values, and we could probably intuit that our answer is going to be 34. But let's just show. So I have 1.1 times 340 minus Vs equals 340. We know what probably the easier way to do this would be to just say plug in some values. Say here, just say, well, let's just put in Vs is 34. So that's 340 over 300, which is about equal to 1.1. Okay? So at this point, you got to be really quick on your feet with the math when you're doing the MCAT, because you know you're crunched for time and you don't get to use a calculator. So look for tricks like that. Always look at your options, because here we could get rid of two options, right? We can get rid of B and D right away, and then it's just a matter of choosing between these two answers that are separated by a factor of 2. 68 is definitely not going to work there. All right, now let's try 759. Always look at your options and see which ones are just not realistic. All right, I'll stop in about 10 seconds. Let's stop at 55. Just guess if you're not sure. Okay, I was going to know pretty well. Yeah, A is the right answer here. A is really the only reasonable answer. You don't have to think about the numbers at all, because it's the only one that's moving away, right? So if I have this really high frequency dog whistle and I want to hear it, I know that the frequency has to drop down in order for me to hear it. In order for that to happen, the source of the sound has to be moving away from me. So it has to be A. It can't be B, C, and D is not right either. That you will be able to hear it if it moves at a speed that's fast enough. Okay? All right. Good. I've seen a lot of problems on the Doppler effect on various practice exams. I mean, you know, it's sort of a crapshoot as to what you get, but it comes up quite a bit on some of the practice exams. Let's look at intensity and loudness. I'm going to skip over the shock waves. You can read it if you want. It's really just sort of vocabulary. There's not really much about this, but when you have something like a shock wave, like in a sonic boom, that occurs when the velocity of your source is approaching or is traveling at about the speed of the wave. So you get a sonic boom, for example, when a plane does what? When its speed reaches what? Breaks the sound barrier. When it comes up to the speed of sound. So as it approaches that speed of sound, you'll get this sonic boom. Yeah. Like when you have a jet. Not that it blows up, but it makes this very loud booming sound. You've never heard that? No? You've never heard it either? You don't know what I'm talking about?
I mean, it sounds.
If you ever see fighter jets do this a lot, if you've ever seen like a fighter jet demonstration, they'll go at really high speeds and they'll just make this loud booming sound. Look it up on YouTube, they're pretty cool.
But it doesn't affect them?
No, the person inside the jet, it doesn't really affect them at all. Okay? It's just how you perceive that. That occurs, the sonic boom, occurs when the speed of the object approaches to the speed of the sound wave. You can think of it as these sort of bows of the wave, the peaks of the wave. It's just they all come together. You can see this in the water too. If you have a boat that's traveling at a moderately high speed, you know, waves have a certain speed that they travel through water. They have a particular speed. And if your boat approaches that speed, your waves will get bigger. I've seen that on boats. It's the same thing. That's like a sonic boom as well. All right, but we're going to skip on ahead to intensity and loudness of sound. The intensity is defined as the power per area. Remember, power is measured in watts or joules per second. This is an energy per time per area. This area is like your surface area. So for example, if you have a source of sound right here, it's putting out sound in 3 dimensions, right? You can in fact imagine that it has these spheres surrounding it, and the intensity of each one is equal to the power divided by the area of that sphere. So you have this speaker that's putting out sound, you move out a certain radius, and then you move out twice that radius. What happens to the area of this sphere as I go from this point, let's call this a distance r, out to this point, which we'll call a distance 2r. What happens to the area, the surface area? Does it get bigger or smaller? The surface area gets bigger, right? A ball this big versus a ball this big. By how much does it get bigger? If my radius is increased by a factor of 2, by how much does my area increase? By a factor of 4, right? Because your surface area of a sphere is that 4 pi r squared. And so, because my area increases by a factor of 4, if I have an area A here, I have an area 4A here. When my radius increases by a factor of 2, the intensity then is inversely proportional to r squared. Since my area increases by a factor of 4, my intensity will decrease by a factor of 4. So if you go to a rock concert, I don't know if y'all go to rock concerts, do you? Y'all don't look like a rock concert kind of type. Do you, Heather? Sometimes. If you go to a rock concert, you want to get far away from the speakers, because if you get up really close to the speakers, it's very, very loud and can damage your hearing. But as you move further and further back, it decreases a lot by a factor of 1 over r squared. Okay? That's good advice. Get away from the speakers, or wear earplugs or something, or big headphones. My son, like he he's sort of sensitive to loud noises. And when we first moved here, we live on the parade route, or like one block off the parade route. And he wanted to go to the parades, and we would go sometimes. But he would always wear his earmuffs because it was too loud for him. And then he wouldn't even go up to the parade. Like, he would be about 50, 60, 70 feet away from the parade. It was kind of strange. Him and his big old earmuffs, sitting way back away from the parade, because he understood that the intensity drops as a 1 over r squared. That it's a lot quieter back there.
He knew that exactly.
No, he knew that.
Okay.
He knew it was quieter. Right.
God, your kids are really genius.
No, they're not really. They're pretty normal. Okay. Now, we have a threshold of hearing. Humans can hear an intensity equal to 10 to the minus 12 watts per square meter. That is our threshold of hearing. We sometimes call this I naught. And the threshold for pain, which is, you shouldn't really reach that, is equal to 10 watts per square meter. Just take a second to look at those numbers, because that's pretty remarkable. 14 orders of magnitude that you can hear from 10 to the minus 12 all the way up to 10. Isn't that amazing? Like, your eye is similarly amazing. That, you know, the human eye can detect like a single photon. If you were to go into a room that was completely dark and there was a single photon in that room, you could detect it. And yet you can also go out and look at the sun. I mean, you shouldn't look directly at the sun, but you can go out into a bright day and you can still see things. We can't build detectors like that, where we can detect such a small amount of a measurement, whether it be sound or light or whatever, and then we can also detect really high values of that same measurement, because our detectors, they would just fry, or they just would not be efficient. This is pretty cool. Look at that. Like 14 orders of magnitude. All right, that's cool. That's really true. Now, because we have such a wide range between our threshold of hearing and our threshold of pain, we don't use intensity to describe the loudness of sounds. Instead, we use what? What measurement do we use? What do we? Yeah, decibels, right. So we use decibels, which is a logarithmic scale. When we're measuring our decibels, it's a logarithmic, and then it's also a comparative scale. This sound level in decibels is equal to 10 times the log of I over I naught. Listen, there's a whole section in the back, and as you get closer to your MCAT, you should probably go through that math section on your own and just make sure that you're up on your algebra and your logs and all that jazz, because you don't use them all the time. You just need to make sure that you're on top of them. And similarly for logarithms. We're not going to spend much time on it now, but when it comes to sound, I think a useful way of thinking about this is that our let's see, first of all, this is our threshold of hearing. So this is our 10 to the minus 12 watts per square meter. And then this is whatever your intensity is. We'll think about this in terms of changing sounds. So if I go from, say, 10 to 20 decibels, or if I have a change in intensity that's equal to 10 decibels, a change in my sound level and a change in my decibels of 10 dB, then that's going to correspond to a change in intensity of equal to 10 watts per square meters. All right, if I have a change in my sound level that's equal to 20 decibels, then my change in my intensity is going to be what, do you think? 20? No, it's going to be 100 watts per square meter. And if I have a change in intensity of 30 decibels, then my change in intensity is going to be what? 1,000 watts per square meter. And it continues on in that way, that as I have my change in my sound level, which is measured in decibels, it corresponds to a change in intensity that is logarithmic in this way. Let's practice a couple of questions that are related to this. Did I bring some? Yeah, I brought some. So we'll look at 673 first. Right up here, a source creates a sound that's observed at 200 watts per square meters. The intensity level decreases by 20 decibels. What is the decrease in observed intensity? Okay, I don't think I explained this very well, so let me try again. A change in 20 decibels results in a factor of 100 change in intensity. All right, so if I have a change in 20 decibels, that means that my sound intensity is going to decrease by a factor of 100. All right, a multiplicative factor, not an additive factor. I'm sorry if that was confusing. So here I start at 200. What's it going to decrease to when it decreases by 20 decibels? What's going to be the final sound? Heather? It's going to go from 200 divided by 100 is 2. Now, if I drop by a sound of 30 decibels, I would drop by a factor of 1,000. So it would go from 200 to 0.2. If I drop by 40 decibels, it would drop by a factor of 10,000. Okay? Is that clear? So what's the answer here? If I'm dropping down to 2, what is going to be the decrease in the observed intensity? Okay, what is it going to be? A few of you have it. 198. It goes from 200 to 2, and so that's going to give us 198. All right. Let's try 674. That's this one down here. We'll skip 660. Let's do 670. Not for superstitious reasons. We're just going to skip it, okay? It's observed at 400 watts per square meters. The intensity decreases by 10 decibels. What is the new observed intensity? Go ahead and do 660 if you're done with this one. And I'll stop here in just a few seconds at 48, 48. Okay, the answer here is A. It drops by 10 decibels. That means it drops by a factor of 10. So it goes from 400 to 400 divided by 10 because it dropped by 10 decibels. Let's try 660 as well. Your sound drops by 20 decibels. Or no. It goes from 20 decibels to 40 decibels. So what must happen to the rate of energy transfer? That's your power. It goes from 20 to 40. What happens to my rate of energy transfer? Okay, look. So if I'm going from 20 to 40, and my sound level, that's the decibels, what is my change from 20 to 40? 20. 40 minus 20 is 40. when I have a change in sound level of 20 decibels, by what factor does that change the intensity? 100, right? So what does that have to do with the rate of energy transfer then? How is the rate of energy transfer going to change? Remember, my intensity is equal to power divided by area. When I say rate of energy transfer, or when it says rate of energy transfer, it's really just talking about the power. Anytime you have a rate, it's something divided by time. Energy divided by time, which is power. All right? So what's the answer, Ariel? Only 3 of you have it. So if you think you have it, you think it's right. Shout it out. What do you think? What do y'all think? You're not certain? Okay. What do you think? Sorry.
Oh, well, that's wrong.
Well, you know it's wrong? Well, don't give it an answer. It's okay if you're wrong. I'm gonna try. Yeah. So my sound is that what you put 100?
Yeah, but that's what I thought, but I only got it because it goes 20 to 100. When you started talking about all that other stuff.
Right here. Okay. Sort of the idea that you want to think about is what is my delta beta? That's my change in my sound intensity level. That's equal to 20 decibels. When I have a change in 20 decibels, that means that I have a 10 to the squared change in intensity. So I have 100 times the intensity that I had before. And so the intensity is directly related to the rate of energy transfer. You gotta watch these things because sometimes just the language will sort of trip you up. We'll look at that with regards to nuclear stuff. That sometimes the questions are written just so that one word can change drastically what your answer is. But that comes with practice. As you practice, it'll become easier and easier. Okay. Let's see some D is right. Okay, let's look at standing waves. We're going to see 3 different standing waves. We'll look at standing waves that are closed on both ends, closed on one end and open on one end, and then open on both ends. We've already seen standing waves a little bit. I sort of introduced them a little bit. Well, let me just remind you that if I have a standing wave, say, in a tube like this, then I have, it'll look like this. I have particular names for these. This is called a node. Remember we saw that like on a guitar string, you have a node. And then we have something down here. This is called an antinode. So a node is just where on these standing waves, remember I have a wave that's traveling and then it reflects back on itself. And it does that over and over and over again. And so I get this one wave that's coming and one wave that's going, and they set up in a system like this. And we sort of showed this last time, but you get a standing wave inside of the box where you have a node on this end, and then on this end you have an antinode. Right? If you have, say, a box that's closed on both ends, but you can't really have sound in that, so typically we would just talk about a string in this case. You get a node on one end and a node on the other end. All right? And then we can also have a box that is open on both ends. And in this case, you're going to get what's going to be on the ends, nodes or antinodes? Antinodes. And in this case, yeah, you'll have one wave that looks like this and another wave that looks like this. So you get antinodes on both ends. We're going to look at all 3 cases, and you'll need to know sort of how you determine what are the particular resonances that occur in these. All right? You ever blown into a bottle? Or you blow into a bottle and it makes a sound? What happens as you put water into the bottle? What happens to the sound? Does it get deeper or higher pitch? It gets higher pitch, right? As you add more and more water, it gets higher pitch. And you can also actually, you should try this, it's very difficult to do, but if you have a bottle and you blow into it, if you blow a very fast wind over the top of the bottle, you'll get a higher pitch sound as well. It's pretty difficult to do. I've never been able to do it actually, I just don't have the lung capacity. But if you blow really hard across the top of the bottle, you get a very high pitch sound. Have you done this before?
No, but flute players.
Oh, yeah. Yeah, a flute player. A flute player is actually this type of tube. It actually is open on one end where your mouthpiece is. Your book talks about this. Clarinets, on the other hand, are like this, where it's closed on one end. So if you blow real hard on the flute, you'll get a very high-pitched sound, right? Do you play flute? Do you? Can you do that with a clarinet? I guess your reed just doesn't permit it, huh? All right. I always wanted to play the clarinet.
I mean, if you go hard enough, it's going to squeak, but it's not going to be
At the right frequency.
It's not going to be a pleasant squeak.
Right. Yeah, I wanted to play the clarinet, but it was kind of a, no offense, but it was kind of like a girly instrument. It still is, huh? Huh?
I always say I was
So I played like tuba. Started out trombone and then tuba. The clarinet's a cool sounding instrument. I like it. Okay, let's look at the one that's closed on both ends at first. Really, we're talking about strings. So if we have a string that's like this is our first harmonic. We're going to call this distance L. How many wavelengths are in this wave? Remember, think about our wave. Our wave looks like this. Think about what a wavelength is. A wavelength starts at one point and goes to that exact same point on the wave. So that's one wavelength. How many wavelengths are in this wave? It's a half a wavelength. So this goes from here over to here. That's a half a wavelength. In order to get a full wavelength, we have to keep going and come over here. So this is a half a wavelength. So L is equal to lambda over 2. If you've ever played a guitar, you can put your finger about halfway and not fret it, like not hold it all the way down to the neck of the guitar, but just sort of hold your finger there, and then you can create the second harmonic on that. Who plays guitar? Anybody? You ever done that? Done the second harmonic where you don't fret a guitar where you push it all the way to the bridge, but you just hold your finger lightly on there, and then you create your second harmonic. And your second harmonic looks like this. There's your one wave, and then there's your second wave. Our distance here is still L. How many wavelengths are here? I have one wavelength here. This is our second harmonic. And then our third harmonic, let's see, does it look like this? Yeah, that's right. Looks like this. And here we have 1.5 wavelengths. So L is equal to 3 halves wavelengths. So this is our third harmonic. All right, so you can tell here that our harmonic, the number of our harmonic, is based on the number of half wavelengths. In our first harmonic, we have a half wavelength. In our second harmonic, we have 2 half wavelengths. And in our third harmonic, we have 3 half wavelengths. Notice that these they decrease in wavelength. Our wavelength decreases for each of these, and so the sound also decreases. The frequency is going to increase. Yeah, Jocelyn? Yeah, that should be lambda, thank you. So the wavelength is decreasing, so the frequency is increasing. This is not the same as filling your water bottle up with water. Okay, this is different. This is like blowing real hard on the flute. That you're keeping your cavity the same length, but you're just changing the number of harmonics that are in that cavity. Okay? So that's for our closed end. Closed on both ends. We have nodes on either end. we can have open on either end. With our open pipes, they look like this. Remember, I have antinodes for the open pipes. This is our first harmonic. Here, my length is 1/2 wavelength. For my second harmonic, on the previous one we had what? Full wavelength, is that right? We can have a full wavelength here as well, but it's going to look a little bit different because I have antinodes at either end. Okay, so this looks funny, but this is one wavelength where I go from here, I go through a full cycle of the wave over here. So this is L equal to lambda. And then our third harmonic, I have 3 half wavelengths. Like that, yeah. All right, here I have 3 half wavelengths, so L is equal to 3 times lambda over 2. All right, here I have 2 half wavelengths, 2 times lambda over 2, and here I just have 1 half wavelength. All right, so the number of your harmonic is the number of half wavelengths. This is just like what we had with the closed tube on either end. It's just it looks a little bit different. The one that's different from that are the closed open pipes, and here we have to count quarter wavelengths. I'll show you. I always found this confusing. Y'all find this confusing? Yeah, I find it a little confusing too. I mean, I don't so much anymore, but just because I've seen it. But here's my closed on one end, open on another. This is like a clarinet. So your clarinet is set up like this. Here, I have a quarter wavelength. So L is 1/4 wavelength. Notice I have a node on one end, an antinode on the other. Node, antinode. Looks like this. This is 3/4 wavelengths. 3 times lambda over 4. This is our first harmonic. This is our third harmonic, they call it, and then this is our fifth harmonic. There is no second or fourth with the clarinet. And then the fifth harmonic is going to have how many wavelengths? 5/4, 5/4 wavelengths. Let's see if I can draw it. Will look like this, and here the length is occupied by 5/4 wavelengths. Okay, let's try a few practice problems on this. Your last page has a couple problems. Let's try the number 710 here. Here you have this string and you're rotating it around so that it creates a waveform that looks like this. Which of these following describes the waveform? Is it the first or third, open at one end, or closed at both ends? Which is it? It's fixed up here on your hand and it's allowed to rotate freely down here at the bottom. All right, just a few more seconds. Let's go to 105 maybe. I'll go to 105. Okay, good. B is right. This is like your tube that's closed on one end and open on the other. So if we were to consider the ones that we've been drawing, it'll be a tube that's like this, and it would have a wave like that and like that. This, by the way, is going to be 3/4 wavelengths. So this is our third harmonic. Remember, we have a first, a third, and a fifth, seventh, ninth, and on and on. But your harmonics, what do you mean?
Okay, so you know the answer to that was a third harmonic. Still open at one minute. I'll show it's the third harmonic.
Oh, well, I don't know, it's a third. Well, your system here is closed on one end, open on the other. The reason it's that is because it's fixed here, right? Your finger fixes it, so I get a node there. And down here, it's allowed to rotate freely. And so that's like an antinode. So our system looks like this, right? That's why this sets up like this, because down here, the wave is fixed at this point. The wave can't rotate, it's fixed at the point where it's closed. But down here where it's open, it's like the string is just allowed to rotate freely, however it will. Now the reason I know it's the third harmonic is because because I know that it's a closed open tube, closed on one end, open on the other, I count the number of quarter wavelengths. So here I have 1/4 wavelength, 2/4 wavelengths, 3/4 wavelengths. So that's how you know it's the third harmonic. All right. With the other two, you count half wavelengths. But with the closed open tube, you count quarter wavelengths. Okay? And that's because you have a node on one end and an antinode on the other. On the other two tubes, you have either a node or antinode on both ends. All right, so it is a third harmonic with a system open at one end. So two things you have to do there is recognize that it's a system open at one end, and then count the number of quarter wavelengths. All right, let's try 711. If you do that one, go ahead to 706. Here we want to know the velocity of the wave. I'm going to give you a little hint. The velocity of the wave is equal to the wavelength times the frequency. Right? We can figure out what the wavelength is. We can also figure out the frequency because the period is given. And then from that, I can find out what is the velocity of the wave. I think I have the wrong answer on this. Oh, yeah. Okay. All right. Guys, notice here that L is not the full length of the string, that L is this distance. Does that help you with what is the wavelength then? If this distance L is 1 meter, what is the full wavelength of this wave? Now this is a half wavelength right here. So if L is 1 meter, what is the wavelength of the wave? 2 is right. Okay. All right. good. I'm going to stop at 248. All right, the answer here is D. Let me show you. So first of all, you need to recognize that my L here is 1 meter, so my wavelength is equal to 2 meters. Okay? And then further, if the period is 0.5 seconds, then my frequency is 1 over the period, which is 2 seconds. Okay? So now I'm looking for the speed. It's going to be 2 meters, that's my wavelength, times the frequency, which is 2 seconds. So the answer is D. 2.5. Well, did y'all have a reason for 2.5? Were you sort of guessing? You put 2.5? Okay. I don't think 2.5 really is it. Let's try 706. If you finish this one, go ahead and do 713 as well. We're with a violin string. The lowest frequency that you get on a violin string looks like this. It's like a pipe closed on both ends. The full length of the string will be 1/2 wavelength. What is the wavelength of this first harmonic? Well, this distance is what? From here to here. This is 30. So what is the wavelength? 60. And the wavelength is 60.
Don't we have to change the meters or the
Yeah, we'll have to change it so it'd be 0.6. Yeah, right. Okay. So our wavelength would be 0.6. All right. What is our speed? Our speed is given. It's 264. It's the speed at which it travels along there. And now I'm looking for the frequency. So we define the frequency based on that. All right. I'm going to stop at 240. Okay, so our speed here is equal to lambda times f. That's going to be 0.6 meters times my frequency is 264. So 264 divided by 0.6, well, that would be roughly what? 264 divided by 0.6. No, it's not 440. It's going to be 880, yeah. 440 would be like 220 over a half. But if you increase both of those, it's going to be 880. Oh, you'll get better with that. You sort of have to be able to look at the numbers to tell what the answer is.
How do you get that?
Do what?
How do you get 880?
Well, it's the frequency is V over lambda. 264 divided by 0.6. That is right, isn't it? I don't know, maybe it is 440. Yeah, it is 440. You're right. I'm sorry. Yeah, so it is, that is 440. Don't worry, I'll get used to it. Okay? All right, y'all, we'll wrap up soon. I know we're all tired. Let's do 713. The one up top here. Which of these represents the fifth harmonic in this closed open system? All right, just a few more seconds. I'll stop at 40. So they are sort of split, but the answer is C. Because I have 5 quarter wavelengths here. I'm looking for the number of quarter wavelengths on this closed open system. Remember, if it was a closed system or an open system, I'd be looking for half wavelengths. I'm looking for quarter wavelengths. I have 1, 2, 3, 4, 5. This is first harmonic. This is what? This is the third. This is 1, 2, 3, 4, 5, 6, 7 harmonic. Yeah. Alrighty. I think that we'll stop there. That's a little early, I'm sorry, but I don't want to go into the next chapter. So we'll just pick up with nuclear stuff, and I expect that we'll just finish nuclear on Monday. It's not a real long chapter, but please do read through it this weekend. It's a pretty important chapter. We won't cover it all in 102, so it'll be good for you to see it here at least. And then we have one more meeting after that, and we will do optics on that meeting, and we won't do E and M circuits at all. Okay? And one more thing. Our test is on the 15th, so that test will cover waves, sound, nuclear, and that's all. So this stuff that we've been doing, and then the nuclear physics that we'll do next time. Nuclear and atomic. Probably you've seen a lot of it in chemistry, but you're not going to see it at all in physics this year. Okay? I was trying to get your test for organic effects. I know it's not like you get that great, but on the MCAT, physically, it's about 40%. I think that was a pretty good score. It was good. Have a good day, okay?